we've already seen conservation of mass and conservation of momentum in integral form, and we just dealt with conservation of mass in the differential form in the previous lesson. So now what we want to do is derive the equation for conservation of momentum in differential form. So I want to take a little box, just like I had for conservation of mass, sides dx, dy, dz. This guy has some overall mass, dm, which is related to density times volume, has a net force, df, acting on it. And so in terms of all this, we want to apply Newton's second law. In other words, sum of forces is mass times acceleration. So my sum of forces is going to be df, mass is going to be this guy. Now first thing you want to do is figure out what's the my acceleration. So fluid acceleration, there's a lesson on that a few weeks ago. What we derived fluid acceleration was dv dt, the local acceleration, plus d plus v, dv ds, the convective acceleration, and then the centripetal acceleration, v squared over r. Now when we did that, it was for the streamwise coordinate using s instead of x, y, and z. That made our lives easier back then. But now we actually want to use x, y, and z because that's what I'm dealing with. My coordinate system is x, y, and z, so I want to change that back into x, y, and z instead of s. So doing a similar thing that we did to derive that guy, acceleration is the full derivative of velocity with respect to time. My full velocity in terms of x, y, and z is some x velocity that depends on x, y, z, and t in the x direction. Some y velocity depends on x, y, z, and t in the j direction. Some z velocity depends on x, y, z, and t in the z direction. And so taking the full derivative, I have a time derivative, so partial v, partial t. And then because x, y, and z depend on time, just like s depended on time, I'm going to get a dv dx, dx dt, a dv dy, dy dt, and a dv dz, dz dt. So I have three things instead of only one that I had for the streamwise coordinate. And similarly, dx dt is my x velocity, dy dt is my y velocity, dz dt is my z velocity. So again, instead of having just one thing, we have all three of them, one for x, one for y, one for z. I can write that in sort of a shorthand way because I have an x velocity with an x derivative, a y velocity with a y derivative, a z velocity with a z derivative. So v dotted with my gradient, that's going to give me those combinations, all acting on my vector v. And this whole combination is what's called the material or substantial derivative, usually denoted by capital D's. But capital D's just mean this, so that's what we're going to need. So in terms of Newton's second law, dF equals dm times a. dm, I know that's density times volume, rho times dx, dy, dz. Acceleration I just got from the previous analysis. What I really want to focus on now is what forces are acting on this block of fluid. So to figure out dF, I need to figure out what forces are acting on my block of fluid. Generally, you're going to have two main forces, gravity and stresses. So gravity, usual force acting down, but instead of saying down is the way I've drawn it down would be negative y. I want to be able to arbitrarily choose my coordinates, so I'm going to have possibly a gravity component in any direction because I want to be able to choose x, y, z to be anywhere I want. Stresses, both normal and shear stresses. So normal basically be pressure forces. So pressure forces, shear stresses, gravity. So my overall force dF I can write as dfg for my gravitational forces and dfs for my shear forces. In terms of gravity, those are the easy ones, so I'll do that one first. dfg is just mass times gravity, again arbitrary direction, so call it guy a vector. dm we know is rho dx, dy, dz. And then, so component-wise, you can break this down into x, y, and z components. dfx is the mass, rho dx, dy, dz times whatever component of gravity is in the x direction. Similarly for y, whatever component of gravity is in the y direction, and z, same deal. So in terms of the stress forces, it's going to be easiest to consider one direction at a time. So x, then y, then z. We'll do it for x, and then y and z. Should be able to see what the pattern is. So we'll do it for x. To do this, we're going to consider all six sides, because in the x direction, there'll be a normal stress on this surface, a normal stress on that surface. There'll be a shear stress on the top surface, shear stress on the bottom surface, shear stress on this front surface, shear stress on the back surface, all in the x direction. So I need to do all 6 sides. And we're going to use a Taylor series expansion like we did in the last lesson for conservation of mass. So that should look familiar. So as I said, my stresses, I have a normal stress sigma acting on the negative x face, so sigma xx minus, this guy pulling out here, sigma xx plus, so again stress sigma xx on the positive x face going in that direction. I have tau xy, or tau yx, again on the positive y face going in that direction, tau yx on the negative x face going in that direction, similarly for z on the front face, tau zx in that direction, and then tau zx minus on the back side going to left as I've drawn it. And so I have 6 stresses, so this is my sigma xx plus, sigma xx minus, tau xy plus, tau yx minus, tau zx plus, tau zx minus. So in terms of my Taylor series expansion, I take sigma xx at the center, which is just sigma xx, and then move it to dx over 2. So sigma xx plus d sigma xx dx times dx over 2, plus some other things I'm going to ignore. So is my Taylor series. That acts over an area. So these are stresses. To get a force, I need to multiply it by an area. So this stress acts on this face right here. So that face will have a area of dy times dz. So that's my area. And similarly for this xx minus, same deal. I have sigma xx at the center. Then I move minus dx over 2 to get to here. I need d sigma xx dx as part of the Taylor series, and then more things I don't care about. Same area, dx dy. And similarly for the stresses, the shear stresses, so on the y and z surfaces, so yx plus, this guy up here, Taylor series, I go up dy over 2 to get there. This area on top is dx times dz, so that's that guy. That guy for the bottom surface, again very similar. And then front surface, tau zx plus, I move in the positive z over 2 to get there, Taylor series it, area here, dx dy, and same for the backside. And then last lesson we also saw that a lot of the stuff's canceled out, so I have sigma xx here, minus sigma xx there, so those guys cancel. I have a positive d sigma xx dx, minus minus another positive d sigma xx dx, so I have 2 of these, so the 2's cancel, and I have dy dz times dx, so overall I have a d sigma xx dx, dx dy dz from the first line. Same thing for the second line, those guys cancel. I'm left with a d tau yx dy, dx dy dz. Last line, d tau zx dx dz, dx dy dz. So that's my overall shear force in the x direction. We do the same thing to the other 2 directions, y and z. Y is going to have normal stresses in the y direction, so sigma yy, as well as shear stresses in the x and z direction. And so very similarly, I'm going to have d tau dx, d sigma dy, d tau dz, dx dy dz for the shear force in the y direction. Same thing for the z direction. I have now normal stresses in the z, so sigma zz, and then shear stresses in the y and x. So again, very similar equation there. So now putting everything together, basically putting everything into Newton's second law, df equals dm times acceleration. So again, you're going to do this component by component. This is for the x direction. Forces, I have gravitational force, so x direction gravitational force, rho gx, dx dy dz. The x version of the stress force, d sigma xx dx, d tau yx dy, d tau zx dz times dx dy dz. Then my acceleration, the acceleration was written as a vector. Again, I only want the x component, so all my v vectors just become vx's, so I have vx's on the top. Rho dx dy dz, that's my dm. Acceleration, again, what we had before, but with vx's instead of my vector v's. So put all that in that equation is what we get, and now I have a dx, dy, dz everywhere, so cancel that, cancel that, cancel that, and I like to write it backwards. So what I'm left with on this side is rho dv dx dt plus vx dv dx dx, vy dvx dy, vz dvx dz is equal to rho gx plus d sigma xx dx, d tau yx dy, d tau zx dz. That is the general form of the x component of the conservation momentum equation. The y and z component is very similar. So again, for the y component, instead of vx, I have vy on the top everywhere. So my acceleration dv dy, dv dy dt, dvy dt, vx dvy dx, vy dvy dy, vz dvy dz, then rho gy. Then I have my stress d tau xy dx, d sigma yy dy, d tau zy dz, and same for the z, vz is on top, gz, my z value for the stress. So those are the most general form of conservation momentum in differential form. They're not very useful because in terms of shear stress and normal stress, those are not easy things to calculate or to measure in the lab. So what we're going to do in the next lesson is make these into slightly better form that we're going to use to actually solve problems.